laser pointer. There you go. Yeah, that's good. Okay, thank you, Rafael, for the introduction. I'd like to, of course, thank the organizers for putting together this very nice conference. It's great to be back here in Natal, and I hope we have more of these in the future. So it was a pleasure to visit old friends and make new ones. So today, let me see if this point, okay. So I'm gonna talk about superconductivity in magic angle twisted bilayer graphene and focusing on the role of long-range interactors. But first, let me just say that I'm from São Paulo, Brazil. This is our campus. So I'm sure many of you had your layover in São Paulo. If you want to stay an extra day, want to visit us on campus, beautiful place to walk, just let me know and you can arrange something. So first of all, let me acknowledge my collaborators in this work. All the results I'm going to be presenting to you today were done by Lauro, who is here in the conference. And also like to thank Jorge Martins at the Federal University of Uberlândia, who taught us all the tricky details of RPA. This paper has been published. The results, most of the results I'm going to tell you about today have been published in this paper last year. So first off, let me give you an outline, and I'll start with, of course, the experimental motivation. And I'm going to make a case for spin fluctuations or magnetic fluctuations as the pairing glue in magic angle twisted bilayer graphene. And in this scenario, we ask what's the role of long-range interactions in the pairing, in the strength of the pairing, and also in the pairing symmetry. And I'm going to use RPA to do that. We heard about the Stoner instabilities this morning, so I'm going to come back to that ending in this context and see one of the key results is that we see that if you calculate the Stoner boundary, you can have a region where actually long-range interactions actually favor superconductivity and take you out. Increasing long-range interactions take you out of the magnetic order phase and go back to superconductivity. It's one of the key results that we get from this model. And at the end, I'm going to tell you a little bit about the pairing symmetry in this scenario. So let's start with going back to basics. Of course, we all know these nice pictures from the 2018 superconductivity paper that came right in the same edition of Nature as a paper showing the mod insulator behavior in twisted bilayer graphene at the magic angle. So early on, there was all these similarities or pointing out similarities between this and the cuprates, for instance, closeness to a mod insulator gap, and then you have the superconducting domes, both with a hole doping and electrodoping. But it turns out that it's much more complicated than that, and I think it became clear. There's some experimental results for order states, even magnetic order that have filling, charge order at a quarter filling, and of course Rafael's favorite pneumaticity and broken symmetries as well. Of course, as we heard from Carl's talk, topology is also an important ingredient that has to be taken into account in presence of these strong correlated Chern insulating states. And I'm going to talk a little bit more about STM and STS experiments in the next slide. But then again, there seems to be a strong electrophoton coupling as well, and we're probably going to hear about that throughout the week. So let me talk about nodal gaps, and this is an important point. Yeah, here. So Carlos talked to us about this paper by the Nudge group, but there is its cousin for twisted bilayer graphene. And in fact, there's a nice, interesting story that I'm curious about. Maybe I'll talk with one of the co-authors, that the titles of the two papers are very much the same, except for the word bilayer in one and trilayer in the other. This evidence for unconventional superconductivity in magic angle, bilayer or trilayer graphene. So I'd like you to hear more about the story. But here, if you go to the paper on the twisted bilayer graphene, what I see is that, of course, they do the measurements of the gaps at both at the charge insulator order at filling -2, around -2, and this one about the filling here is -2.4. You're already in the superconducting case, and the fitting for this pairing gap with regular BCS S-wave is not so good, but if they do a fitting with a nodal superconductivity, you get a much better fitting. So there's the case for nodal gaps in the systems. We also have some evidence for competing superconductivity and magnetic order in this reference here. And more exotic things like spin textures and skyrmions that essentially imply that you do have low energy spin, or at least magnetic degrees of freedom and cytomagnetic fluctuations within these parameters. So, so this is the case for some sort of nodal gap, perhaps with spin fluctuations. And also regarding long-range interactions, we're really motivated also by this work. And by the way, most of these works, the first authors are either in the audience or not the first authors, but there's authors of these works in the audience are participating in both the organizing committee and probably hear more about these results throughout the week. And this one is an interesting case that show that if you can essentially tune Coulomb screening in this system, and in fact that affects the superconducting behavior as well. So whenever you have a stronger screening of the Coulomb interactions, you get a stronger, a larger value of the critical temperature here, especially when you are now with a reduced screening, strong Coulomb interactions, you get a decrease. So it tells us that you can, in principle, have some degree of control of the screening of the Coulomb interactions in the system, so that you might even think of the Hubbard parameter U to be tunable. That's one of the key aspects that we're going to be discussing. Okay, so our goal here is, given all this background, that if you assume from a point of view that you have nodal-like superconductivity from spin fluctuations, what's the interplay of both the band structure, the non-interacting band structure, and tunable, let's put it this quote-unquote, tunable long-range electron-electron interactions to the pairing gap and the symmetry in magic angle twisted bilayer graphene. Yes? Yes. I'm going to show you some phase diagrams that precisely do that. Yeah. At the end, yes. Okay, so what are we going to do? So we need to start with a microscopic model, and we're going to choose this one that essentially gives us the correct band symmetry. And that's essentially what we need. We need reliable Fermi surfaces, at least for the non-interacting level. The thing is, every time I mention this model, is like to a community like that, or even to individuals, is like walking into a saloon in the Old West, and you were a stranger, and everybody looks at you and go for their guns, right? Because there are problems with this model, and I know that. So don't shoot me. Here, the thing, of course, I know there's veneer obstruction. You need to go to very large hoppings, and we got that. But our goal here is that this is a simple model to implement, which at the time for us was important, and it gives us the correct bank structure for the flat bands, right? Of course, there are one extra point in this paper that attracted our attention, that we know by now that's probably not completely correct, which is the fact that the Coulomb interactions are very long range. So the decay with distance from the on-site Coulomb interaction to the fifth nearest neighbor is very small. And probably this is a net artifact of the veneerization effect, but okay, we took this and made something out of it, saying, okay, what if you have, say, maybe not this strength in the fifth nearest neighbor Coulomb interaction term related to the on-site one, but you have somehow the ratios fixed, and maybe the whole thing is screened down. So our model for the interactions, and here I'm including both the on-site at, say, a AA point here, we're going to be called A, or BB is all U, and the nearest neighbor, the first next neighbor Coulomb interaction term, I'm calling U1. So these, I'll keep them as tunable parameters, right? So if you take U1 equal to 0, you have essentially a Hubbard model on hexagonal lattice. Now you can keep the long-range interactions with some ratios to say this value here. At Cochino's paper, you get these ratios. We have, of course, the results I'm going to show you is by keeping these ratios fixed, but we did also some analysis by changing these ratios, and we saw that the actual number doesn't really matter as long as you do have a modulation in the effective Coulomb interaction as a function of momentum, and that's going to be the key important point. So for me, in this context, what these long-range interactions do is essentially give a Q dependence on the Coulomb interaction, and at the precise dependence of these Q interactions is more important than the actual ratios that I'm showing here, right? So, okay, so this is my interacting model. And on top of that, we're going to do, of course, we have to write down the different terms in Q space so that we can plug that to our RPA equations. And so here we take the Fourier transform, and we can relate these Fourier transform matrix elements to what in the RPA languages are usually related to the so-called charge interacting matrix or the spin sector interaction matrix that are related to essentially to writing this Hamiltonian in a form that you are more directly writing this in terms of density and spin correlation functions. And then you have to work out all the algebra to connect what you get here to here, and that's one of the contributions that we did for this model, and that's all Lauro's work. But at the end of the day, this is just a mapping, right? So once you have these numbers here, you can calculate these and calculate these two. Okay. So this is sets up the non-interacting part and the interacting part for our RPA calculations. And then what we can do is we can calculate the spin and charge susceptibilities at the RPA approximation using bubble and ladder diagrams. And at the end of the day, what you get if you have a single band Hubbard model like we saw on Andre's talk this morning, these would be just numbers, right? So, or functions, right? And then you have here the non-interacting accessibility. You plug in your, say, the Hubbard interaction here, and you get your RPA expression. Of course, when this becomes equals to 1, you have your Stoner instability. Now, since we have a two-site, two-layer model, this will have more degrees of freedom. So instead of functions, we have matrices. So we have to now calculate these matrices with in all these components. Even the non-interacting one will have a structure. This will also be a matrix. So the Stoner criterion here will be essentially related to how these different matrix elements diverge or not. Okay, but once we calculate the spin and charge susceptibilities, what we can do is to build the pair interaction in the singlet channel. We did some calculations for the triplet channel, and we see that they're much weaker. So in this model, the singlet channel dominates. And so we plug in those interaction matrix for the spin and charge sectors. We plug in the RPA spin and charge susceptibilities, and then we can calculate the kernel, essentially the pair interaction, and we can plug this into a pairing gap eigenvalue equation in the linear approximation. So all these are momenta at the Fermi surfaces or the different pockets sometimes if you have them, but essentially we sum that over the Fermi surface. This gives us a eigenvalue equation, right? Where the this is dead apparently. Yeah, sure. Not at this level. Yes. I think we could include that, but then it would be mixing. Essentially, have to calculate a more general susceptibility for this case. Yeah. Yes. Yes. Yeah. And in general, that will happen for the spin one. Yes. Okay, here it's all at zero energy. So that's the linear. So it's not the full Liushberg kind of pairing equation. So we're focusing everything on the Fermi energy. So this is an important point, that even though at the end of the day, what I'm going to get is these eigenvalues that in principle, the larger the lambda, the larger the TC is. At this level of theory, I cannot, any TC that I calculate with these lambdas is essentially gibberish. So you would need to do a full spectral treatment to get, say, a mean field and to get the correct TC. Yeah. Okay, so that's we're gonna have some plots on say this guy at different k minus k prime, but this is a very anisotropic Fermi surface, as you mentioned. So there will be peaks in it different away from zero, right? So nesting is going to be a very important element here as well. So and because you definitely don't have circular Fermi surfaces in this system. Okay. Yes. Yeah. Yes. Yes, that's the. Okay. So that that will probably that will probably favor magnetic ordered phases, depending on the strength, right? And we have to think about it how we could include those, because then you essentially what you're saying, we're going to have to add more terms to my interacting Hamiltonian. It's not just density like yes. Yeah, then I have to think about how to do that in RPA. I'm not sure if you want. Yeah. Yes, that's a good point. Yeah, no, we haven't thought about that, but yeah, in principle you could. I mean, that probably would add matrix elements to these that we're now setting to 0. That's an interesting point. We perhaps could, like spin flip, right? Spin flip is one. One important thing is that, now I think that not for this work, but for the other work, if we include terms like that, maybe the spin susceptibility will start depending on, say, long-range interactions as well. At this approximation, they don't. It doesn't, right? So that's a very interesting point. Okay, so this is essentially the setup. So our goal here is to essentially plug in all these numbers and solve these eigenvalue equations and see what the leading and subleading values for lambda, and also at the end also I'm going to be looking at the structure of the gap as well. Okay. So Stoner instability. So of course this, as I mentioned, is a matrix. So we can define the so-called Stoner parameters for both the spin and charge sector. And whenever one of these and becomes 1, so this is like a diagonal matrix, one of these becomes 1, or its maximum value becomes 1, either on spin or charge, then you have either a magnetic Stoner instability or a charge Stoner instability, and that's essentially, that's as far as we can go. Beyond that, we know that there's some magnetic order, but is outside the realm of RPA. Essentially breaks down. But we know we can have a pretty good idea when the boundary is, and that's going to be a really important parameter or the characteristic of our results that we're going to explore. So just to remind you, whenever you see this alpha x equals to 1, means that you have a Stoner boundary in our system. Okay, so now let's start by checking, doing the calculation of different filling. So we're going to start, say, a very small hole filling, very close to the Fermi energy. So the Fermi surface looks something like that. And here's the boundary of the Brillouin zone, of course. And then what you get, if we take a phase diagram, putting the Hubbard interaction U on the horizontal axis and the ratio between the first Coulomb interaction between nearest neighbors and U on the vertical axis, we get a phase diagram like this. So for U1 equals 0 means that we have no long-range interactions. So essentially by increasing U, you get an increase in the lambda, or essentially you make superconductivity stronger, very close to the Stoner boundary line, which is this black curve here, when you have the maximum of the alpha in the spin sector equals 1. So of course, the closer you get to this line, you have larger and larger values of omega, so that you have stronger susceptibility, strong superconductivity here. But once you get over to the other side, you have a magnetically ordered phase, and superconductivity is destroyed. So there's of course a coexistence or this competition between magnetic this is dying. A magnetic lower phase and a superconducting phase. So for low dopings, the superconducting phase is very narrow here. So you quickly get to the boundary line. And one other way that you can also, by increasing the long-range interactions, you are still, say, if you get a nu here, increase the long-range interactions, you also hit the Stoner boundary on the side. So the long-range interactions also can contribute to the Stoner instability, and that's essentially the what you get for this very small filling factor. Now, so this is singlet pairing, and now you mean the symmetry? Yeah, we're going to get to that at the end. So I'm going to do some, it's nodal. Yeah. Yes. Okay. Mm-hmm. Mm-hmm. Okay. If we look at the Stoner parameter for the charge sector, we see that is way down here. And in this approximation, the spin sector essentially wins. So the instability in the spin sector will come before the instability in the charge sector as a function of U. Now, there is a good question of whether you can have a situation where that's inverted, but probably you would need to start off with a different kind of pairing at the onset. So yeah, sure. Yeah. They're separate, right? So it doesn't depend on. So if I write this point here, right? So P is sublattice and sigma is spin. So it involves both of them. So in principle, should be. It's just the density interaction as general as you can have, right? No, yeah. Yeah. No, there's no interaction. Yeah.
So I'm going to, the discussion is great, and we want discussions to happen, but I also want to have lunch. So I'll just ask, it's fine to continue this, but let's just move on a little bit.
Okay, yeah. No, these are great questions, because, I mean, we have some interest in continuing this work, and all the comments here will be welcome. So now if I go to the other extreme, which is a very high filling factor or whole filling factor here, say -3, then what you get is a much larger superconducting phase. You still have your Stoner boundary here, and this is essentially an effect of the density of states being larger, right? So but the shape of your Stoner boundary is essentially the same. It monotonically decays as a function of U or U prime, and we're going to see why that is in a moment. Now, if you are sitting, oh yeah, and this is what I was mentioning about the Stoner parameters, say for different values of U, as a function of U1, it will eventually get to the Stoner boundary, and the spin one is much stronger than the charged one here, in this sense. Okay. So now, if you're sitting exactly with the Fermi energy at the Van Hove singularity here, you get filling factor about minus 2.5. What you get is you still have your superconducting phase, you still have your Stoner boundary, but now the Stoner boundary is not monotonically, it does not decrease monotonically with you. It has this duckbill shape kind of structure where you might have some regions for very small long-range interaction effects where if you start from a magnetic order phase at a given u and you increase the long-range interactions, you go back into the superconducting phase. And that's really what started us, because it happens precisely if you are sitting at the Fermi energy at the Van Hove singularity. And then we're trying to understand what, in this region, what's happening. Why do you have the superconductivity favored by increasing the long-range interactions relative to you? Okay. Yeah. Yes, yes, yes. Just sitting, you know, the Fermi level at like the bands are rigid in a sense. So yeah, so you know there are different effects that could be happening here, like randomization of the bands due to interaction. All that we're not disregarding. We're keeping the non-interacting model essentially fixed, right? So what's going on here? And if I look now at the Stoner instability parameters as function of u1 over u, sitting, say, right here, what I get is precisely what I just told you, like 1.81 here. You get, for u1 equals 0, you get a magnetic order. As increase u1, I cross over to the superconducting phase, so alpha less than 1, and if I keep increasing u1, I go back to the magnetic order phase, and this is actually almost a kink, right? So what's going on here? And here is where the interplay between band structure and long-range interactions actually are playing in order for this effect to happen. So the first element here is that we see very strong nesting precisely near the endpoint. And I'm going to show you some diagrams showing that later, but that means that the pair interaction has a peak, a very pronounced peak, very near to the endpoint. So in this situation at u equals 0, what you get is that, say, what's happening here at the Stoner line is that you have whatever the non-interacting susceptibility value is at the endpoint, right, or near the endpoint, which is a peak due to nesting. And this is going to be of order 1 over u, because if you don't have long-range interactions, this guy is just going to be u. And these things are comparable, and you get essentially 1. Now, if you increase u here, what you would need, so increasing this guy, and this guy is essentially fixed, you would need, now you are in the magnetic phase, so in order to get back into the Stoner line, you have to increase u1, right? For this guy to go back into the Stoner phase. So why do you need to increase u1? Because as soon as you include long-range interactions, what you get is a dependence of u with q or with k. So if I go back here, if you have u1 equals 0, your dependence on u with k is essentially a constant. It's just equals 1. It equals u right here, which is 1.8, right? So it's just as a flat line. as soon as you get long-range interactions into the picture, now you have a Q dependence on U. And in some regions of the Brillouin zone, the effective Coulomb interactions will be smaller than U, and in others it's going to be larger. Now, where this happens, when you have the sort of attractive component from long-range interactions making the U of K smaller than U, precisely at the endpoint. Precisely at the point where here you have very strong interactions, very strong contributions to the non-interacting susceptibility due to nesting. So in this case, when you increase U1, you are decreasing U of K right at the right position where you have a strong peak in the non-interacting susceptibility. That means that in order to get back to the Stoner criterion, you have to increase U so that this thing now will get of the order of 1 over this one. So you have a positive slope as you vary U1 and you are in this region here. Now, if you keep increasing the long-range interactions and you get to this point here, what you get is that you have still a dependence on Q, and is much more pronounced, but now the nesting at the endpoint essentially is reduced. And what is more important is what's happening at Q equals 0. And at Q equals 0, then you have a positive contribution from long-range interactions to the effective Coulomb interaction as a function of Q. So this is no longer negative. And then you get to the usual case that, I mean, if you increase the interactions at the same value of U1, you have to decrease U1 in order to go back to the line, and you have now a negative slope. And in between these two slopes, they meet, and that's what makes the shape of the Stoner boundary non-monotonic. Notice that this is happening for very, very small values of the long-range interactions. So in this case, that's what I mean, that you don't need, like in a model that proposes a very strong value for the very long-range Coulomb interactions. Something very, very small already does the trick. So, and the other thing is that this happens precisely at the whole singularity, where the nesting effect is very strong. Okay, that's a good point. So then the question is whether the screening would affect differently both the on-site and the long-range ones. And yes, and then our guess is that this essentially would rescale the parameters somehow, but you could have a situation where the ratio, or those ratios that I'm talking about, say the Coulomb interaction at very long range relative to the first neighbor, actually changes due to screening. So that would be, especially if the screening depends on Q, right? And it's not just a static number. That would be also another interesting follow-up for this work. So let me just show you what happens then at the very strong feeling for holes, where you now your nesting is quite far away from the endpoint, and if you keep increasing the value of U1, now both the nesting point and the U, they happen at a momentum where the U of K is always larger than U. And in this case, this is always larger than U. You just get a monotonic decrease or monotonic shape for your Stoner boundary. Okay, another way to see this is if you look at a cut throughout the whole Brillouin zone, right? Depending on the filling. So let's just start with the filling at -3 here. So these lines are precisely when the effective Coulomb interaction, the function of Q, equals to U, meaning essentially this line here, right? This line here. So these points are where the magenta lines here. So very close to the gamma point, this is positive. Between the gamma and the M point, this becomes negative or less than U. There's a small region here around K where this thing is positive again, and then it becomes negative again, and then positive again. So this is essentially shown here in this situation. So whenever you are inside these pockets, you have U of T larger than U. Your crossover here is attractive, so these attractive contributions. And it's inside these very small pockets near the K points, you have U of Q larger than U again. Now, if I look now at the nesting, right? So at this filling, the nesting essentially given by this green arrow here. So you are still in a region where U of Q is larger than U, so nothing interesting happens. So if I keep changing the filling factor going up with my Fermi energy, at some point the nesting vector will approach the circular magenta line, and right at the Van Hove singularity you will surpass it. So here, that's where the duckbill shape happens, when you have a nesting vector in a region where U of Q is less than U. Now, if I keep doing that, there's a very small region where this condition persists, but at some point, my nesting vector will go back inside the magenta curve, and then I'll have just a monotonic Stoner-Cartesian curve that I was showing you, and nothing more interesting happens here. So how much time do I get? 0, okay. So just to answer Andre's question, let me show you a quick slide about the pairing symmetry of these things. So how calculate the pairing symmetry? And this is not in the paper, it's something that still need to work out perhaps a better way. So let's say I'm here at precisely at the Van Hove singularity, and this is what my Fermi surface looks like. I go and solve my eigenvalue equation, and I get my lambda, and I also get my pairing gap. Now I plot my pairing gap as a function of K, and this is what I get. This is the leading eigenvalue, and they're very close to that, the subleading one. Essentially, they're pretty much the same. So the right thing to do is to look at this combined picture as my pairing gap. The first thing that you notice is that it's nodal. I mean, there's nodes around here everywhere, right? From positive to negative. And now the question is, of course, I have to figure out which symmetry does it have, or the reduced symmetry that it belongs to. So, and of course, I can do that as a function of the long-range interactions as well, right? So, say I pick this one, and I say, okay, I want to figure what the symmetry is. So what Lauro did was to go back to the character table of the D6H and get all the 12 irreducible representation, right, basis functions for all of them, and see, now plug my pairing, my gap function, and see which one fits the best. So, and then the computer says, oh, well, for this case, E1U has a larger contribution, so this is your best guess. And okay, so he does that for every U and U1, and then for each one, he comes here and plots a point, and then he does that as a function of U1 and U, and this is the picture that we get. So in the orange here we have essentially the gap function following the U1U irreducible representation, and here the B2U. And that changes depending on the filling. So if you are now closer to the zero, to this point here at minus 0.81 filling, you get a different symmetry, and you can do this phase analysis, or this phase space for the symmetry of or a phase diagram for the pairing vertex symmetry for each one of these. So that's as far as we got. We know that for very small filling factors, E2G is the dominant one. Now, at the Van Hove singularity, you have a clear competition depending on the ratio between the on-site interaction and the long-range ones between B2U and U1U. And right down at -3, now you have E2G appearing in B2U1 also appearing. So this is the summary of my talk. I'm not going to be bothered, but I'm just going to be doing a advertising for Laur's posters on a different system, but we did pretty much the same ideas for this transition method decalculationites, where he essentially looks at the Stoner criterion and see if you can explain these superconductivity retrend behavior by just looking at the Stoner criterion. And with that, I'd like to thank you for your attention and be happy to take some more questions.
Great. We're going to open for questions here.
Quick questions. The parameter U0, UU seems to me a bit too small, because that is the self-interaction of one of your Vannier wave functions. Typically, people consider it's like 20, 30 MeVs.
Okay.
That's what, for instance, Andrei Bernevich proposed.
That's a good point. So again, if you look at the different papers, depending on the screening, and the like, Bernevik's papers will give you something more about that, like 60, 50, 60. Here we use, for these calculations, we use things that are closer to what you get. Oh, I don't have the number here. What you get from the Cuscino paper, but yes, I agree. Then the question is that if you increase U in our calculation, you would get a Stoner instability right from the outset. The point is that depending on screening, you might get a reduced value of U, of course, depending if you can do that.
And now the last question. Your susceptibility, in principle, in twisted bilayer graphene, the susceptibility is a matrix in a reciprocal momentum space. There are Ucla processes. They are gone into your calculation. I think it's because you're missing the internal structure of the Vannier functions, which is related to the questions Oscar and Andrei were asking you. Other terms in the effective interaction.
Okay, that could be. That could be.
Andrei, then Oscar, super.
My question will be quick. Sorry, returning back to superconducting gap symmetry. Suppose that you are right at Van Hove point, as you did, and I'm at weak coupling, and let me take U1 equal to 0, just for sake of argument. You're at small u, then presumably the gap is the largest at Van Hove point. Or you get a gap which vanishes at Van Hove point. So what's the answer? Again, I'm at weak coupling, I'm at Van Hove density, and I want to look at the gap around Van Hove points. So what just a question about clarifications. So Van Hove points are, I guess, the ones then you have a crossing between Fermi surfaces, right? So what is the gap there? Leading term, yes. So
so this is the full.
This is a full Fermi surface, yes. So this is exactly where the gap, right?
Yeah.
So you get a gap which would change a sign between Van Hove points.
Yeah. So let me show you here. Yeah, here in the leading case, you have a gap here. In the subleading case, you have a gap here. Right.
Let's look at the leading case. Just to understand one thing.
Yes.
So you have a gap which is finite
Here.
at Van Hoff point, and would change the sign between Van Hoff points. Is it true?
Yeah. Have to. Yeah, it should go to 0. Yes.
But
Right there.
it's exactly the question. Does the gap goes to 0 at Van Hoff point? Because I guess at E1 representation gap goes to 0 at Van Hoff point.
Okay.
Or it's finite. Because if it goes to 0, then I immediately ask a question how you get a singlet state, spin singlet state with gap, which is supposedly linear near Van Hoff points.
Oh, I see. Well, so if I understand the question is how, I mean, we start from a singlet pairing from the outset, and that's what you get, right? So yeah, it is 0 in some of these crossing points, but not in the others, right? And actually, between this one and this one, it actually changes sign. So it's not 0 everywhere.
If you look only at Van Hoff point, does it look like D-wave gap that it has?
Well,
D-wave gap in hexagonal form surface.
yeah. So if I
Plus minus 1.
yeah, it would be something like that, right? So so here is 0, here's not, here is not again, but here's 0. So that would be the structure.
I just want to get a clarification on the assignment of the IREPs. If I remember correctly, you said something like there's some sort of a code which determines what is the largest overlap, but it wasn't quite 100%.
Yeah,
So does it mean that you actually have a mixed IREP or you have a pure IREP?
That's a mixed, yeah.
Okay.
See, it's, yeah. So, yeah. That's, love to discuss that. That's something we have been struggling with, right? That's precisely one of the reasons we haven't published this data. Is precisely we have to come with a better way in order to. Yeah, sure.
You need to make it just to be a little careful, right? There are an infinite number of business functions.
Right.
Sure.
Yeah.
Right. So the fact that it's better to just apply the symmetry operations of U and see
And see what you get.
and see if you get.
Yeah.
Because there's an infinite number.
Sure.
Yeah.
Okay.
Yeah. In other cases, what helped is that you take 2 leading eigenfunctions in a given rep and try to fit with 2 rather than with 1.
Okay.
And then normally percentage goes up.
All right.
Pretty.
Okay. Thank you.
All right, last question.
So I just wanted to ask, did you see how does the phase boundary evolve if you were to artificially truncate your interaction? So you would go, let's say, from only on-site to keep adding the...
All right, that's a good question. Let me. The whole thing is what would happen at the Q dependence of the interaction, right? So I think you can. Let me go back here. Yeah, this one. So as long as you have a structure like that, you have. Yeah, not in this case, but as long as you have a Q dependence on U, and at some point you have a nesting at the non-interaction stability precisely at that point where this U has a minimum, then you get a phenomenology just like I asked. Of course, if you start changing the ratios between the U's at long range, then this black curve might not even have a minimum here, right? So I think the best way is that, okay, can you design a structure of U's that gives you a wiggly function like that? That's where it would be your best chance of observing this non-monotonic behavior in the sonar line. Thank you.
All right, let's thank Luis one more time.
Thank you. Thank you very much.
So I was a little bit lax